This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Eberhard Wolf. I'm sitting here with Florian Gilcher. Florian, welcome to the show.
Hello, Eberhard.
Florian is the CEO of Ascera, a consultancy here in Germany. He is co-founder of Russ Berlin, and he is also part of the global Rust community group. He has written quite a number of articles and blog posts about Rust. So obviously our main subject today will be the Rust language. First off, why did Mozilla even start Rust? What niche does it fill?
First of all, Mozilla didn't start Rust directly. It was the hobby project of a Mozilla research employee, Graydon Hua, which was later adopted by Mozilla Research themselves. The niche it fills is a replacement for the systems programming languages that Mozilla currently uses. Mozilla is a heavy user of C and C++, and Rust is an attempt to make these programming environments safer. So for a lot of parts, they're currently using it for their browser development, but also for all their other native targets.
Concerning systems programming, there are quite a few other languages that are also becoming popular in the last few years. For example, Go. So what's the difference to those other new popular languages?
So the main difference to Go is that Go has a runtime that is necessary to run Go programs. Rust doesn't have one in the classical sense. So there is no garbage collector in the language. There's no runtime library that you need to link.
And where would you use Rust? Obviously, Mozilla has projects that are using it, but why would I use it over other languages?
I would use it anywhere where currently C is still popular. For me, who's originally from the Ruby world, Rust fills the niche of being another language that you can drop down to when your scripting language becomes too slow. Rust can be used to implement dynamic libraries that you can later use to the FFI of your language. So these are classical places, or just for standalone web server or CLI tools.
We already spoke about how Rust started off as a hobby project. Can you say a few more words about the history and where it comes from?
The history is a pretty long one, so to say. Rust was first publicly released in 2010 and committed to GitHub. And back then, the language looked much different from how it looked like today, which was also the reason why I joined it around 3 years ago, because it was definitely a programming language in the making, and you don't have that very often. That you can look at how they evolve. And at the beginning, Rust was a language that was fully focused on concurrent programming, did ship with a runtime, did ship with primitives for concurrent programming. And I think because Go was at the same time becoming popular, that shifted a lot, because Go was already a concurrent programming language with a runtime. So Rust moved away towards, we want to bring all these kind of stuff to lower parts of the stack.
How did the evolution of Rust actually take place? I mean, usually there is like a language specification, then you implement the specification, and then you extend later on. Is that also what Rust did, or did they use a different approach?
There used to be a write-down of the language specification at some point. There was an implementation of the compiler, first in OCaml, later replaced by a compiler written in Rust, which was then constantly evolved on. Very early on, there was a release process introduced, which was later changed, but all Mozilla projects need to have a release process and an RFC process. So even before the language was finished, all changes needed to be proposed, all larger changes needed to be proposed. And we still have a track record of all the larger changes, why they were implemented or why features were cut before we released stuff.
Were actually features removed from the language, or was it just extended?
There were a lot of features removed. In the beginning, I just mentioned that Rust doesn't have a garbage collector. When it was first released publicly, it had a garbage collector. which was optional, which was then later removed. One interesting thing about the whole evolution is that there was always a large project that was developed in lockstep with Rust, which is Servo. Maybe touch on that later. So a lot of theories about how the language could work we were actually able to test on a large project. For example, the removal of the garbage collector we tried to implement Servo without GC. And when we figured out that this works, we don't need this. We had the GC as some kind of, okay, we're not sure if our system holds, so we can always grab into the candy box and use garbage collection. And that was removed after we managed to find out that we can implement Servo without, so probably the language can live without.
Interesting, because usually I think languages are just extended and grow features over time, and removing stuff as fundamental as a garbage collector is quite unusual, I think. What's the syntax like? Nowadays it seems there's either the language is C-like or Ruby-like. So what about Rust?
It's a little mix. So it's C-like in the sense that we have curly braces and everything. It has generics that look like C++ Java. The syntax with angle brackets, and it is an expression-based syntax like Ruby, so you don't need explicit returns. Everything, like the last statement of an evaluation, is also the return of that evaluation.
So is there like a natural parent language that Rust evolved from, or that it was based on?
Not quite. It is the first productive implementation of the kind of type system Rust uses that I know of. So there's definitely some research work that predates it. It has influences from a lot of other languages. A lot of the engineers that work on it have a C and C++ background, so there's definitely some of that. And it also shows that if you see newcomers to the language, you can, with some experience, tell which language they come from. Kind of shows that it's a mix of many styles that people can then also reuse.
So talking about research, it seems that Rust is more like a language that was grown from the practical side of things, or does it have like a strong academic background too?
It's an interesting mix. It's written at Mozilla Research, but with the definite goal of going towards practical use, especially after it was decided that the language should actually be released as a 1.0. It started to become far and far more practical, and it has a lot of convenience features that show that everyone working on the language had ample experience with other programming environments.
Let's talk about the features and what the language actually feels like. So first of all, is Rust type safe?
Yes, Rust is type safe. Safe Rust will never segfault. It also, on top of that, gives safety guarantees to concurrent programs and uses the type information for a lot of compiler optimizations. So yes, the type system is at the core and it's important.
Is the language statically typed or dynamically typed?
It's statically typed, and it does a lot of checks during static at the static point of compilation. It does have almost no dynamic features at runtime that you don't have to opt into. Maybe explaining that later, but the Rust compiler catches most errors it catches at compile time.
You said that you are from a Ruby background, and obviously Ruby is dynamically typed. So don't you feel like that you're limited in your freedom and your flexibility if you switch over to statically typed language?
Not quite. It has certain trade-offs. Sometimes you have to work for a lot of things more than you feel like you'd have to in your favorite dynamic language. On the other hand, it also gives a lot of guarantees. I know at every point what type I'm using. I know at every point what's going to happen if I do this and this function call. It has a very predictable performance characteristics, and especially when it comes to concurrent programming, Rust gives you a lot of help in catching unsafe patterns there.
So is Rust object-oriented?
No. It may look like it sometimes. So you can define functions on top of structures that do take a self parameter, which looks a lot like Python. but this is more of a syntactic convenience at a lot of places. It doesn't have methods in the sense that I can send messages. It has no message passing at all. So all the object-oriented features beyond having methods are completely missing.
Also inheritance, I assume.
Inheritance is missing. At least structural inheritance is missing. We're going to cover traits later. Traits can depend on others, which is a form of inheritance, but you cannot describe data structures in the sense of this is the same, but with a few additional fields.
But you can have structures, it seems, but then you would have functions separated from those structures in a different...
Yeah, functions and state are always separated.
We already sort of spoke about it. So what are structures or structs?
Structs are, if you come from C world, basically what you know as structs. It's the description of a data structure and its memory layout. So the memory layout of data structures in Rust is currently not defined. It may change over compiler versions. Can force the compiler to lay it out like C would lay them out. But there's not much more beyond that.
Why would I do that? I would have thought that, accessing the struct and relying on how it's in the memory is sort of hackish.
The layouting like C part is just there for being able to pass the structure over to a C program and back. So that's an FFI feature. Other than that, for example, compiler optimization reasons, fields may be reordered. This is really just for, there's certain places where I want that. Also, well, for example, if I interface with my operating system, they still got C APIs. They expect something to be in a specific layout, so we can provide. That's a heavy use case of Rust at that point.
I see, yeah. To interface with C, that makes a lot of sense. So what about traits?
Traits are implemented on top of structures. So I can have a trait that defines a certain set of methods that take the structure I implement it on as, for example, the self parameter and do certain things with it. We also call these functions methods because they do have self parameter as first parameter, but they are independent of the data structure. I later create the mapping of this data structure implements this trait, this trait, this trait, and they generally are used in the sense of I have an equal trait. Equal means that all data structures of that type can be compared, or I have other traits that mark the structure for this is safe for sharing, this is unsafe for sharing, and all these kind of things.
How does that actually work? Would I say, okay, this is a struct that implements that equal trait? Is that how it works?
Yes.
Okay, but when I have an equal trait, actually, I only say that there should be a method somewhere that allows me to compare two structs. It doesn't say anything about the data structure, does it?
Exactly. So they're independent of the internal structure.
Oh, I see. So a trait wouldn't say that this data is part of the struct. It would just say that there are some methods that you could use on it.
Exactly.
So in the case of the equal trait, I would need to implement like an equal method for all of the types, all of the structs that would implement that trait.
Exactly.
Then there are algebraic data types. What about those? How does that work?
Algebraic data types are unifications of other type. For example, the classic is the option type, which we also nowadays in Java and Scala or in others, which has two forms. It's either I have some data or I have none, which avoids having to have a null pointer in the language. So no data is basically a value in the sense of programming. And especially on all interfaces, I see that this is optional or not, compared to Java, for example, where basically any parameter can be null, and I have to check for that all the time. In Rust, I can express this is optional, this is not, and you need to check for it. If it's optional, you need to unwrap that option at some point and find out what's inside, or if there's nothing.
And would that be implemented as a struct, or is it a separate concept?
We call them enums. So there's the enum keyword, which introduces all variants of that enum. So the option enum would basically be it's optional for some struct, and then it has some t or none as the two variants. There's another important one of those types, which is the result type, which is used all throughout Rust, which has the two variants there's a result or there's an error for any kind of operation. And the other nice thing is because they are types, you can implement methods on them. So options and results can be combined.
So there are no exceptions, obviously, but that is something that you would do with the results?
In general Rust, there are no exceptions, yes. We do have some form of exceptions, which is called panicking. So there's always the case that a program goes completely amiss. In that case, we panic. And that's implementation-wise equivalent to a C++ exception. So the stack gets enrolled and everything, but that's not for normal program flow and cannot be recovered.
So you already said that an option would be an option of T. So it seems there is parametric polymorphism and generics in place. Is that how it works?
Yes, we do have generics. I also told that at the beginning that we have a generic syntax that's similar to Java. So structs and functions can be generic over their arguments, and option is an example. So you have option T, which is either a sum of that type or none. Another interesting fact about the optional type, by the way, is that its data layout is similar to having a null pointer or not. So you can pass it again to see just normal as you would usually use it.
What about macros? What are they?
Rust has hygienic macros. Rust can be a rather verbose language, so macro use is very, very common, especially for patterns where you have a number of structs with a very, very standard implementation of a certain trait. People often write a macro for providing that implementation with just the fill-ins of the struct name and all these kind of things. For example, when it comes to equals and all these kind of things, people just don't want to implement equals for each type and then all its subfields and everything like that. So their macros are used very often. There's also a number of libraries that provide, for example, parser combinators, which use macros for getting a cleaner interface there, depending on if you like macros.
What kind of operators would be implemented?
They would, for example, implement combinators for parsers using a macro. So, for example, I have a parser that parses a string.
How do those macros work? Is it like in C where it's just text that get expanded, or is it somehow a higher level programming feature?
There's a sublanguage. Basically, for Rust, for any kind of macro, they take a certain set of tokens and you need to provide the macro with a description of what these are. Are they keywords? Are they fields? Then this macro gets expanded at that point. As I said, they're hygienic macros, so they're not just text replacements. The compiler will, at expansion time, check whether the code coming out of that makes sense and point towards errors in the macro expansion. That can be a little verbose because macros might expand macros and all that, but the compiler can actually detect errors within the macro definition that you're hitting and not in the sense that you need to find out what happened and then deduce from the final source code.
So would you call them idiomatic? Is that something that you would use, macros?
Macros are idiomatic, definitely. For example, just the standard print line in Rust is a macro because standard by foot implementation of printing to standard out would be getting a handle to standard out, locking standard out, writing to standard out, interpolating a string that you write to standard out, and we got that all wrapped into a macro. So they're definitely idiomatic. There's also another commonly used macro which is called try, which takes one of these results and if it is an error, immediately returns out of the function that is called in and otherwise gives you the value back. So it breaks early and returns the error out of a function or gives you the value back. And that's a very, very common one that you couldn't live without.
So the two examples that you gave are more like, seem to me more like parts of the language core, so to say, or let's say the standard libraries. Would you write a macro yourself? Is it a feature that you would use as a normal developer or just for library developers?
Yes, there's definitely macro sets as libraries, which are important and interesting. And as I said, Rust can become rather verbose at some point. So providing macros for standard patterns is definitely idiomatic.
Before we started the interview, you said that actually you thought that there were some issues with macros. So can you explain that?
I have personal issues with macros. I think macros point a little towards flaws in the language, for example, extreme verbosity around some features, and are a fix that I don't like that much, but that tends to come from the point that I'm from the Ruby world where a lot of these things can be expressed in the Ruby language itself. I don't see any need for macros in Ruby because it usually has that boot phase for all applications where you can change the whole runtime system, which we don't have in Rust. So it's probably the fix for that.
What about functions? What are functions in Rust?
Functions in Rust are either just normal functions as you know them. So we have bare functions that just take parameters and return. Functions can be generic. So you can say, well, I have a function that does something on anything that's comparable or all these kind of things. Functions, the same as all the others before, can be forced to follow the C API of the platform. So you can use them as callbacks to C libraries and all these kinds of things. The functions are pretty much standard. I can also have them on a trait, for example, with the implicit self-parameter. We do have closures in the language too as a separate concept. Functions and closures are separate, especially because functions don't close. I can have inner function definitions within a function, but functions don't close. There's a strict separation within the language.
Can you elaborate on the difference between a closure and a function?
A closure has access to the environment around the definition of the closure, so it can access variables that were outside of the closure. If you have an inner function that you defined, for example, for a callback or something like that, you cannot do that.
So you would either have access to sort of the outside world or not. And Rust supports both. That's what you said, right?
Yeah, Rust supports both.
What about higher order functions and all these advanced function programming paradigms?
A bit tricky currently. It's usually not used. What we do have in the sense of functional programming is that our iterator API uses the map, filter, and reduce paradigm, but I wouldn't call that functional programming in the sense that you return functions that are pre-bound to parameters and all these kind of things.
But at least you can pass in functions as parameters to a map function that would then execute the function on each member of an array or something like that. But not really the advanced features that you would find in a true functional programming language.
Yes.
Okay, at the very beginning you said that Rust was actually quite useful for concurrent programming.
Yes.
So what is Rust's approach towards mutability? I mean, obviously, if you talk about concurrency, it's very easy as long as you don't have mutable state. So, those are two related issues, I would say.
Rust's approach to mutability is rather direct. There's this classical problem in concurrent programming that shared mutable state is problematic. But if you have a close look at the statement, the problem is that sharing and mutability at the same time is problematic. Okay. So what Rust does, it takes these concepts by themselves and says, okay, so first let's approach mutability and make it a first-class concept of the language. So every variable binding that you introduce is either mutable or not mutable by the keyword mut. And if it's not mutable, you cannot use it, you cannot change it in any way. And every time you pass access to some of your values to another part of the program, you also have to mark whether it's in a mutable fashion or not. Okay. So it's kind of on the question of whether we're a programming language that models immutable data or immutable data, we're both in a sense. But it's a first-class concept, and the compiler will deduce different things based on the mutability of your values.
I would actually use a keyword to mark it as immutable variable, right? and then the type checker would catch issues if I have, mutable stuff or immutable stuff that gets passed to something that should be mutable.
Yes.
So it's an extension of the type system.
It's part of the type system. So at a lot of places, the mutable, for example, sharing is a type. I'm getting a bit ahead of you here, but sharing is a type in Rust, and the mutable fashion and the immutable fashion are both different types that follow different rules. And that's a very important part there for the safety guarantees that we're going to talk about later. But also in the non-shared data case, that's already pretty interesting because there's a very good blog post by one of the server engineers that says if you have a sufficiently large single-threaded program, you're already running into problems that are similar to concurrent programming. For example, I pass a value into a huge library and I cannot safely figure out whether that library will mutate it or not. And in Rust, you can safely do that because the interface says, okay, you get it in a mutable fashion or not. And I can then assume that you have mutated it or need to assume that you might have mutated it.
Okay, so it actually gives me more guarantees about the code, and therefore it makes it easier to figure out what the code actually does.
It's also very explicit. That's the advantage of Rust's verbosity. It's very explicit at all places, and especially around mutability, it's always clear if you can change something or not.
I think we will put a link to the blog post in the show notes, so you can look it up later on. Okay, excellent. That's the part about how to separate mutability and immutable data. There's also a concept of ownership. So can you talk about that?
So every time you introduce a value into a program in Rust or allocate it somewhere, either on the stack or on the heap, you're the owner of it. And there can only ever be one owner of every piece of data. That's fundamental to how Rust works. That's statically guaranteed. And that also means that we can statically ensure that we find out when you're not going to use that value anymore, and then remove it from memory and drop it. The ownership follows rather simple rules. You either have it, and then you can do everything with that value, or you can pass it on. For example, in the sense of when we're talking about mutability, if you own a value, you can even decide, okay, this is immutable, but I'm just going to make it mutable. Because there's no other party involved. The static guarantee is you have ownership, can do whatever you like with it. And once it drops out of scope, it will be removed, or you explicitly call a function that removes it.
Yeah, I found that interesting. So you said once there is no owner of some data, it would get removed. That sounds a lot like garbage collection. But before you said that there was actually no garbage collector in Rust.
Yes, that's statically proven at compile time where the value needs to be removed. So we get a little bit into terminology problems there with whoever we talk to. Like a lot of people that come from the Java world are pretty much fine with if you say, okay, the compiler will introduce that call during compile time, and they're like, okay, that's no garbage collection. Others, anytime they don't have to call free by themselves, they're more like, okay, but this is garbage collection in some fashion. The problem there being that the term garbage collection not being very well defined. So you can already see that in Python. Python has reference counting, and some people call that garbage collection. Others insist that it's reference counting and not in the sense of a garbage collector. For us, that is all happening at compile time with opt-in towards runtime parts. So if you need more, because you can only have one handle on any kind of data, this is sometimes impractical. We have a special kind of pointer, which is part of the language standard library, but not in any way special in Rust. That is, for example, a ref-counted pointer, which allows you to have multiple handles on it. And anytime people drop these handles, a counter is counted down. But that's opt-in at all times.
But how does that fit to the ownership paradigm? So because in a way what you're saying is in that case there are multiple parts of the code that would have a pointer to that piece of data, and once all those are gone, then it would get removed from memory.
The way it works in that sense is I pass away ownership to the RC type, then I own the RC, and can get handles of that, which I own again. So the whole system runs pretty deep. I can always say, okay, I own something and I wrap it into another thing that I own, which gives additional possibilities to work with it.
So what's RC?
RC would be ref counter.
Oh, okay, I see. So basically I'm taking that piece of data, I pass it on to the ref counting, and then I can pass on those references to other parts of the code. And they would own that, but I would still own the original data. What about borrowing?
Borrowing is the companion to ownership, because always passing on ownership can be problematic. I need to give ownership to all parts of the program. They need to give it back. And usually what you do in most C-style languages, you would just pass on the reference to other parts of the program. And this process in Rust is called borrowing for the reason that there's additional rules involved. Behind the concept is basically just passing references somewhere else. With borrowing, it's again the same. I either borrow immutably or I can borrow mutably, which allows the other party to do whatever they want or whatever's allowed with it. And as I mentioned before, the mutable borrow and the standard borrow are different things. So for example, if I have a trait that implements functions on mutable borrows and some on immutable borrows, it might be that I cannot call all everywhere depending on how the piece of data I have was shared with me. So it allows for certain operations to be done or not. And the important rule in borrowing is I can share something immutably through borrowing as often as I'd like, or I can share it mutably once, but never both of it. So it's never allowed that a mutable borrow and an immutable borrow is active at the same time. And that's statically proven, again. And the problem obviously being the concurrency problem. If I have an immutable borrow, I want to be sure that it's actually immutable. If I read it twice, it must be the same value. And that cannot be guaranteed if someone else has immutable borrow active.
Right. What about send and sync? That's another concept for concurrency.
So send and sync are markers that the compiler deduces or that you can implement yourself if you are absolutely sure that you built something that is one of these things. Send is I can send a value between concurrent parts of the program. Like I can pass ownership between like a thread and another thread, which means it's not available anymore in one of those, but available in the others. And sync is there's some synchronization primitive provided around the value, which makes mutable sharing safe. So Rust, for example, will tell you, so I have one example where I implement a small, very simple server, which is single-threaded and writes to a hash map. And at some point, you can start making it multi-threaded and you start introducing threads, and suddenly the compiler comes along and says, okay, now you cannot concurrently write to that hash map with that additional work, because a hash map by standard is not sync. And then you can again wrap it, for example, in a mutex. A mutex, for example, provides sync for all the internal parts. So these are just markers that the language provides. But for example, the mutex that's implemented on top of it, it's not a language feature, it's a library feature.
There is also safety. So what does the term safety mean in the Rust world?
So safety means memory safety. So safe Rust programs will not produce any illegal memory accesses and segfault. There's a couple of little confusing things around that. For example, memory leaks are safe. They're not an illegal memory access. So the safety guarantee here is really we don't crash in that sense, and we don't provide any illegal memory operations. And yeah, no double freeze. Also, and I have to say, in the case that a program has to unwind because it's been panicking at some point, there's been an out-of-memory access or something, we also make sure that all values along the stack are properly removed.
How would you call unsafe C code, for example?
There's an unsafe language, which is introduced by the keyword unsafe. If you use it, you can say unsafe, open a block, and do unsafe operations within it. For example, then you can do pointer calculations and all these kind of things, producing raw pointers, using raw pointers, and all that. So there, most bets are off. It's still safer than in a lot of other languages. There's still compiler checks going on. For example, if two things that you are using are the same memory size, so we still have checks there. But yeah, and this is, for example, used for calling into C, but there's also some points of the Rust language where unsafe is used to provide implementations for things that are more efficient than what you could write in safe Rust. This is pretty rare. It's usually around data structure primitives, where there's known patterns to very quickly implement them using raw pointers. Yeah.
What I'm wondering about is, this seems to be a rather different approach from many other languages. So are you aware of any other languages that do similar things, or is it really Rust specific, this concurrency model?
The concurrency model itself is rather Rust specific, especially the approach of having just these kinds of marker traits and these kinds of rules around mutability and sharing, and not actually implementing something in the language. So, for example, Go has channels. They're part of the language. We don't have channels as part of the language. We have tracking from the compiler whether things are safe, and you can implement the abstractions on top of it yourself. For example, there's currently a large project going on called Tokyo, which provides an event reactor for Rust programs and is using a lot of these primitives, but is completely implemented outside of the Rust compiler or outside of the standard library.
What's the result of that? I mean, if you have a C program, you can be pretty sure that there might be some buffer overflows and stuff like that. And even in a Java program, you might have memory leaks. And, in particular, the threading model is rather complicated. So what's the result? Are Rust programs, in your experience, very stable, very safe, or are there still issues?
They're usually rather stable. Also on the memory leak side, I think the fact that in Rust you have to work for getting shared access to values also makes sure that you don't accidentally get it. We also catch a couple of other bugs. So in general, yes, Rust programs are memory safe, and I rarely see memory leaks. Crashes are very rare on standard programming use. We also catch a number of additional bugs that are pretty often seen in other languages. For example, the nice thing about the ownership model that we have is that it does provide iterator invalidation, for example. Because suddenly, if you get hold of an iterator of a collection, we have additional info because we know which part of the program will just pass it on. We know which one is going to mutate it. We know which one is going to own it. For example, we cannot pass it on twice accidentally.
If you're talking about the problem that if I have an iterator of a data structure, then concurrent system might change that and then my iterator becomes invalid. Is that what you're talking about? That is obviously solved in Rust.
Yes. You can never get... one of the things there is that you need access to the data structure in a mutable fashion and access to an iterator at the same time, which is usually prohibited by most Rust APIs.
Is the language itself extensible? In what way? I mean, we already spoke about macros. That sounds like something that you can basically use to sort of extend the language. Are there other features?
There's a nightly feature called... So Rust has a nightly compiler and a stable compiler, and the nightly compiler has certain features that the stable doesn't have. There's a nightly feature which is compiler plugins, where you can implement other things on top of the language, get access to an AST and all these kinds of things. But this is slowly moving, under my impression, towards providing extension points. So what we currently have, for example, is custom ways of deriving certain features on structure is easier, so that you can, for example, just say derive JSON decodable on top of a struct, and then you can decode it from JSON. But this is something you don't really want to have as a language feature, because that would fix you on one implementation of this. So this is something we're currently working on providing, and that's landing soon. As far as I understood, compiler plugins will at some point be available as a standard Rust feature.
Is Rust compiled, or is it an interpreter, or is it using some kind of virtual machine?
It's completely compiled. All of what I've described is completely working at compile time. All the safety guarantees are happening at compile time. The only thing that we have as a runtime system is, well, the implementation of stack unwinding.
So I actually get a binary that would be directly executed just as I would in C or C++.
Yes.
Okay, I see. And what's the tool chain? So would I just use the compiler, or would I need to use some kind of build tool in addition?
We ship a package manager that's called Cargo, implemented by the people that implemented Mozilla before, so it's not their first attempt. And so we did a community survey.
I would use that to get the libraries, right?
You would use that to get the libraries and also to compile your program. So it comes with a set of subcommands. So you get a configuration file where you give in all the dependencies, all the development dependencies, and then you get a set of subcommands, build, run, test.
So I would use Cargo and Rust, the Rust compiler, and I'm done.
Yes. And the Rust compiler itself ships with some support for testing, so which can be driven through Cargo test. So after you run Cargo init, you're completely set up for test-driven development in Rust.
How would I make sure that my application actually works, let's say on Windows, when I'm on a Mac and compiling it on a Mac?
So you can cross-compile. Cross-compiling to Windows is probably a little bit of a problem because for cross-compiling you need the base libraries, so there's some setup involved. But we do ship the standard library and the core libraries implemented for all important targets, including iOS, Android, Mac, different flavors of Linux, and certain embedded targets. Windows is a first-class target for Rust.
So are you sharing the compiler backend with, I don't know, the GNU tools or anything like that, or is it, custom built?
It's LLVM in the back.
LLVM. Okay, so what's that?
That's a low-level virtual machine, currently implemented by Apple mostly, which is also behind the Xcode toolchain, CLang, and everything. And it's basically a compiler toolkit and comes with, compilation support for multiple targets. So in general, the target support in Rust is roughly where Apple and Google are big at. Support is currently good. If not, we need to make sure that we provide.
You said LLVM is like a virtual machine, but that doesn't say that it's actually generating bytecode that would be interpreted at runtime.
No, it's a compiler tool. It still has VM in the name, doesn't really resemble a VM in the end. It's just the name of the project. It still has the VM in it.
Just to confuse people. Can you give an overview about the standard library and what it offers?
First of all, there's a core and a standard library of the language. The core library is what is needed to run all kinds of Rust programs, in the sense of you need to have an iterator implementation because there's a syntax for it. So you need to provide that, and then there's the standard library on top of it.
What do you mean? The language forces you to have specific parts in your library?
There's a core library that defines a certain set of types that must be there for the compiler to compile a Rust program, even without any kinds of libraries. For example, send and sync are so core to the language, they are defined there. It's a library though, so if you have any need to replace it, you could implement your own and pass it to the compiler, and it will first compile the core library.
It sounds to me like it sort of feels like a language feature, but in fact it's not. It's implemented in the library.
Yeah, so we have the core and the standard library. The core comes also with a few additional conveniences. The option and the result types, for example, all these kinds of very, very basic important types are in there. The standard library itself implements your standard fare, file access, some collections. It doesn't implement a collection API in that sense, so there's no generic collection API. Because of an interesting particularity of the Rust language that's not easy to provide currently. The problem is that we also need to track, if you have an access into a collection, we need to track on how long that collection is alive, whether that has vanished. So this makes a standard collection API like Java map or something much, much harder than they have. So just be aware that standard collections is a set of standard implementations of collections, but it's not like you can replace one against the other simply by just hiding it behind a trait and just working on top of it.
So I'm not sure whether I understand what you're saying. So there are, maps in place, right?
Yeah, but the standard library would provide a hash map or a tree map or something, but you would have to, I'm using a hash map here, I'm using a tree map here, and not import some larger interface that says use standard map and use one of these at that point. So it's very much bound to the concrete implementations there.
But I mean, if you look at a map, all the maps provide getting data from a specific key and setting data to a specific key. So it seems like you could abstract a type, and I thought that is what traits are for, but that doesn't work.
It would work. There has been an implementation of that before Rust 1.0. It was cut because it wasn't deemed very convenient and very hard to extend. And so what was decided that it's currently not being implemented until we have found better ways to implement that. It's also a problem of a language. Sometimes you don't fully understand the patterns that might emerge from a programming language you define at some point, or maybe features are missing for all these kind of things. So it was opted for reshipping the data structures in a proper implementation, but not the glue on top of it.
Imagine that I actually do want to change the implementation of a map that I'm using. What would happen? I mean, obviously I would need to say, okay, I'm using, let's say, a tree map instead of hash map. That's the example that you gave. And then what's left to do?
You would probably at some point change a lot of the accesses to the map too.
Because actually the methods would be called differently?
No, the methods will be called the same. Some might behave differently, and there's additional methods, for example, on the hash map to get hold of an entry of the hash map in a different fashion as for a tree map. So there's a lot of specialized methods on top of that, which you probably would like to use. So this is more where this is diverging. They all have get and set.
Is that an issue in real life, or is it just sort of only damages the aesthetics of the language?
I haven't found a lot of people that mention that as a real issue, because many programs that we have probably fall into the class of, okay, I'm providing some kind of functionality like lookup for something, and I'm using a hash map in the back, and I'm hiding that behind another data type altogether. So changing that it's an amount of work I can guess. In about 1 or 2 hours, I have replaced that. There's larger complaints about the collection API that's basically just that you cannot control memory allocation currently. So if you want to control memory allocation, you would need to use your own implementation of one of these primitives. But it's a work in progress in that part. It's just not that anyone would complain that what's there is bad. So that was the thing we wanted to ensure, that the things that we have are usable and usable in the general use case. For example, the complaint about the hash map for a lot of people is that the hash map that we use is DDoS safe. So it uses a hash function that is DDoS safe, which might not be the fastest one. And some people want fast ones. But no one's complaining about the current implementation being bad or the interface being bad. So that comes a little bit from the youngness of the language. I wouldn't say immaturity, because the implementations are mature. It's sometimes a little hit and miss. So an implementation is there or it's not there. If it's there, it's good. That's what we want to ensure. And that's also the reason why general collection traits were, after quite some discussions, cut before we released the language.
I think that makes a lot of sense. I mean, looking at what works in practice is probably like the most important thing. Okay, so we spoke about the standard library. Obviously, every language has quite a lot of libraries. Are there any highlights among the Rust libraries?
I really like the current implementation of serialization and deserialization, which is called SERDE. It's a general serialization and deserialization framework that you can use. I'm a huge fan of it because it's rather convenient to use. There's a couple of web frameworks. One of them is called Iron. That's becoming pretty popular, that are efficient and working well. And I think the current highlights are really Tokyo and Futures. So they're implemented in lockstep. Futures is the Futures implementation for Rust. It's just the interface for what a future concurrency primitive is, which can be combined as you know, the futures as concurrent operations for future operations can be combined, forked, and all these kind of things. And it's pretty interesting to look at how that looks like in a language that has, for example, no exceptions, that uses results and errors as primitives everywhere, and all these kinds of things. And Tokyo is a library where you can run these futures on, because futures are really just this outward interface that you can implement later. That brings a little bit of confusion. A lot of people think it comes with something, but you actually, if you implement a future, you need to get something to run it on. And the reason why I find it interesting is because there used to be a time where these have been language features, and it was decided to not have them as language features. And now a lot of the people that have been implementing these language features 2 or 3 years ago are now implementing them as libraries. So it's an interesting piece to look at. For those that are from the Java Scala world, is that Tokyo is heavily inspired by Finagle. So it's basically a Finagle clone.
Obviously, you're working with Rust. So what are like typical applications that you yourself do with Rust?
So I'm currently working on a CouchDB client. That's more or less experimenting for me, because I'm heavily interested in CouchDB, and I would really like to have a more low-level library to CouchDB than what's currently available in all the programming languages. It's called LazeRS. And for my day-to-day use, I implement a lot of command line programs in it. There's also a great command line parser in Rust, which is called clap. It's highly recommendable. So there's a couple of projects where people basically write the third or fourth implementation of something they like doing, and then coming over to Rust, and you really see the quality of people that know what they're doing things for the second or the third time around.
What are other people doing with Rust? What are some popular projects that are actually based on Rust and using Rust?
So obviously there's the 2 Mozilla projects, there's Servo and Firefox. So the relationship is that Firefox is slowly starting to adopt features from Servo, which was is a new implementation of a browser rendering engine by Mozilla, which is heavily using the concurrency guarantees that Rust gives. There's something that's sometimes missed. I forgot to say that before. The nice thing about the mutability tracking in Rust is also that it ensures that at any point where you're using a value, you know if you need lock-free access or not. So for a lot of places you can actually get away without locks, which is a much stronger thing for concurrency. And I know that Firefox, for example, has problems of the kind of, we are locking something because we think there might be concurrent access, but there's not. And this tracking makes sense. But Firefox is currently mostly using URL and media parsing libraries written in Rust, because those are also libraries that are very, very easy to run into memory safety problems, like string being too long, field being read too long. A lot of these formats communicate, okay, this things about memory layout.
Which brings me back to the other issue. I think we sort of covered it already. So there is an interface, FFI, for foreign function interface. That's for C, I guess, right?
Yes. So you can generate libraries that follow the standard platform ABI, and then compile Rust to a dynamic library that can be then linked from your Ruby, Python, whatever program. And that's a rather common use case. And I know a lot of companies that kind of have a Rust library around for doing some heavy lifting in their Rails program. The standard example there being Skylight, which has been around for 3 years as a Rust user or something. because they have picked Rust even before it was stable, for saying, okay, we don't have enough C++ engineers here, but we need some embedded fast library in our product. So what we're going to do is we use a language that's similar to C, as easy, embeddable, and embedded in our program. And what they do is they do metrics gathering in Rails applications for their clients, which is something where you absolutely don't want to ship something that's segfaults, because that brings down your client's web service. Absolutely don't. And there we're seeing that a lot. So there's been, for a long time, basically people using Rust and Python and all these languages said, well, okay, Ruby and Python, if it becomes slow, we just replace it with a piece of C. But I've never seen that happening, because once you ask people the question, okay, but can you make sure that this doesn't bring down our whole machine here? They're like, okay, maybe we just deploy another machine and get along with it. And this is a supported and often made use case. Just to cover a couple of others, we have Piston, which is a gaming library, which I can't cover because I never used it. Habitat by Chef is a new way of deploying applications onto infrastructures, which ships the libraries together with the application, and the whole tooling around that is written in Rust. We see a lot of tools in the DevOps world being written with Rust nowadays. Timely data flow is more of a research project that I just want to drop the name of. It's implementing data flow through infrastructures with collecting of data and doing computations of data. It's a huge framework, but there's a lot of writing about it by the author. Finally, we have operating system development in Rust. So we're very happy about that. There's a growing community of operating system implementers. There's one called Redux, which already boots into a graphical shell and all these kind of things. So you could use it for something. There's two very nice ones, Intermezzos and FilzOS, which are meant for teaching operating systems. So they come with a lot of documentation on why the implementations are like this, but also give interesting insights on how to find safe abstractions for a lot of these things. For FilzOS, there's a great blog post about how to implement the memory management of the operating system in a safe fashion. And finally, Mozilla has started a project which is called TOC, and it's an embedded operating system currently just for Cortex processors, but it's getting along.
So let's talk a little bit about the community. So how many committers are working on Rust right now? Do you have any idea?
So it depends on who's a committer. So we have more than 1,000 different people contributing to Rust C, and currently regular committers are between 5 and 10. There's some people employed at Mozilla. There's some people that work on Servo that also commit to the compiler and all these kind of things. But it's definitely a busy project.
But most of the people actually work for Mozilla. So it's sort of a Mozilla-founded project.
It's a bit more the other way around. There's a lot of people contributing, but definitely the people with large contributions most of the time work for Mozilla, because being paid for working on something just gives you a head start. But yes, there's a set of people working at Mozilla, working on the language design and working on the compiler, and also contributing to it, and also contributing to a lot of the library ecosystem around it.
And how is the project organized?
So we have a set of teams, which you can find on rustlang.org/teams.html. And there's a core team which cares for all directional decisions around the language. They basically have the final say on everything, because someone in the end needs to have it, but rarely exercise it. They have to do all the work around the RFC process, for example, argue with people about things, plan new features, and work, basically implement them. There's a language design team and a tooling team that's split off working on these respective parts. Same process though. If there's a language feature to be implemented or to be proposed, they have to go through an RFC process. There's a documentation team. We have also one person working full-time on documentation of the language, and we generally get good marks on that, although there's still a lot to do. Like implementing documentation for a standard library in a proper fashion is a year work.
So you said that you heavily rely on an RFC process. So how does that work?
So you go to github.com /RFCs, and there's a sample document on how an RFC should look like. And you fork that and you start writing your proposal for anything you'd like, which could be new methods for a standard library, for a standard library type, changes to certain behavior, although they need to be backwards compatible. We're pretty strict on backwards compatibility.
But before you said that, Rust actually removed quite a few features.
That was before 1.0. So that was the reason why before 1.0 there was a lot of feature cutting going on for months. The question basically was, do we want to commit on this and keep this around for years? A lot of stuff went out of the language and a lot of stuff was changed. So nowadays that's not possible in the general case anymore. From time to time, there's the case where, for example, someone finds a soundness issue in the type system, which needs to be fixed, which might lead to some breakage. But that's the point where you really need to discuss whether that's something you need to keep on.
How do you organize the community? Obviously, you're working in particular on that part of Rust.
So there's a second set of teams. One is the community team, which I'm on, and the moderators team. The moderators team is there for, day-to-day moderation of forums or subreddit and all these kinds of things. We don't use mailing lists anymore, especially because they're bad to be moderated. We found that a lot of new people don't really care about mailing lists that much anymore. And the community team itself works in a bit of a very distributed fashion. We meet every week. The meetings are open. They're in our time zone every Wednesday at 6 in the evening. And there's another meeting that sometimes happens that's more for the Asian time zones. So we try to be approachable there. It's open in our IC channel. You can always join in and ask questions. And there's also a GitHub organization in which we plan new stuff. And the general angle of approach to the community team is, and that's been by far the best, we have an email. You can write us any question you want about Rust, the compiler, what do I know. If you don't know who to approach in the project, write a mail to the community team and we bounce you off. And that's been a very, very simple and very workable approach.
How do you automate the community? You said that this is actually something that is very specific about the Rust community.
It's always hard to say we automate the community, but we automate certain aspects of it. For example, we have 1,000 committers, and I recently had a look at some of the numbers. Usually a pull request in the Rust compiler sits for 6 days, mean. And we merge a lot of them. So there's a lot of automation involved there. And the first thing is, if you ever write a pull request to any or an issue on any of our repositories, there's a bot which is called High Five, which just says, "Hi, you're contributing. Here's a few things I have to say about that, and the assigned person to this issue is someone." And then High Five just picks a person and assigns that issue to someone. And instead of thinking too much about that, about who's responsible for this thing, High Five just assigns anyone. And that person's responsibility is either to handle the issue or to come up with a person that should handle it, which makes sure that we have no unassigned issues anywhere and everyone's cared for. And that's surprisingly simple and surprisingly effective, because a lot of problems that open source projects have are these kinds of lingering issues that are in no man's land, where no one knows who's actually going to deal with them, or everyone thinks that's someone else's job, and we just assign the job to someone, and we automated that. And we have a merge bot. It used to be called Bors on Rust C. I think it's still Bors. There's a re-implementation of that called Homu. And what it does, it tracks commits to master, or it makes the commits to master. So what it does is on any pull request, you can enter R+, as this is positively reviewed, or R-. And if you get an R+, what it does is it checks out the pull request, it checks out master, merges them, runs all tests, and when all tests pass, merges all this back into master. The advantage is that it holds a queue of these requests. So you can review 6 or 7 pull requests, and then the bot will just start taking the first, doing that process, committing to master, and after it's done, continue on. Because the problem there is that merging a pull request usually breaks all others, because then they're based off a different branch. And all this busy work is taken care of by that bot by saying we have a standard continuous flow where each of these is merged after another. And if anything happens, it will just come back and say, okay, here, I've got a problem. Yeah, and finally we have Crater and Glacier. Crater is important for the backwards guarantee. So if we have the feeling that there was a language change that might lead to problems. So for example, you change something in the type system and you know that there's an edge case which will then stop working. There's always the question, is anyone using that? Or how much breakage would that lead to? So what Crater does, it pulls all crates of our package repository, which is crates.io. I guess we haven't introduced the term, so a library in Rust is called a crate. And then it compiles all of them and makes a report of how many of these have failed, especially have there been any regressions towards previous things. Like we obviously have some libraries that are broken, so they don't compile anymore. So it's more like it tracks regressions on an ecosystem-wide scale so that we have an idea on how many problems we've introduced. And finally, there's a nice little project called Glacier, which tracks all compiler errors. So if someone finds a compiler error, we write a small test case in Glacier that shows the compiler crash and if it's fixed or not.
You said that you focus on backwards compatibility. So what happens if one of those crates fails to compile because you did a change to the language? Would the language change be rejected? Because that seems to be what backwards compatibility would be about.
Depends on the kind of change. Usually, yes. But as I said, for example, in soundness, for type system soundness fixes, there's always the question on, okay, there's one crate that fails and 5,000 that don't. But this is an issue where, for example, you could escape one of the safety guarantees of the language. This is definitely a debate to have, especially at the current state of the language, if we want to keep that around for the next few years. So, yes, this standard would be reject.
So, how do I start?
You go to community.rs, and that's a page we just introduced last week, and it holds a lot of info on where to get started, where to find people to connect with, which are the forums, where does the standard library documentation live, all these kind of things. Other than that, just go to rustlang.org, download whatever we have there, the compiler, cargo, and all these kind of things. And then you just install it, run cargo in it, start coding. If you don't want to do that, there's also an interactive interpreter, or no, an interactive compiler, on play.rustlang.org, where you can try out the language before even installing anything. So a lot of meetups provide hack and learns. So here in Berlin, our standard meetup is we just meet and code instead of someone giving a talk. Like at the current state of the language, probably a talk is less interesting than a person giving you a short introduction on how to approach your problem with the language. So we try to have more people meeting regularly, just learning together. Also, our ISC channel gets great marks for being friendly, and we have the habit of... So it's frowned upon to tell newbies that they should just read up before they ask a question. So there's a lot of people around that usually have time for answering your questions.
Anything else you want to add? Anything else I forgot to ask you?
So in general, the community team is always searching for people that want to run a meetup or work with us, especially in the southern continents. So Australia, Africa, South America. We're very happy to have a rather strong community in Brazil, but that's growable. So we want to be a project that's not just based around Europe and the US. And finally, if you have some kind of specific hobby, I don't know, some people care about certain technologies, we'd like to have an implementation in Rust. We need a lot of libraries currently, so if you want to be the first person to provide a certain library to a programming language, now is the time. And finally, if you are using Rust and we don't know of you, I would be happy if you could write to the community team, because what we also do out of quality control reasons is we do interviews with production users. We'd be very interested in interviewing you.
Thanks a lot for the interview, and I wish you all the best concerning Rust and the Rust community.
Thank you. Stay safe.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.